Hello, everybody. Thanks for coming. Today, I'm going to talk about how we power Optiver's real-time market insights with Databricks apps. So I'm going to give you a bit of an overview of what I'm going to talk about today. First, I'm going to give you guys a bit of about introduction about Optiver, about who we are. Then I'm going to talk a bit about our dashboard journey and how we came about to this project. Then I'm going to talk about various optimization techniques that we have done to improve user experience. First is on the ingestion side, then after that is on the dashboard side. Before I continue, raise your hand if you heard about Optiver before today. Oh, wow, that's a lot more than I expected. So for those who don't know about Optiver, if you go to our website, you will see that we are a high-frequency electronic trading firms. We are a global liquidity and market makers. We trade in various exchanges across the globe, and we also trade in various asset classes such as options, futures, and ETF. So what is market making? So as a market makers, we provide the buy and sell prices continuously to the exchange. Regardless of market condition, we're always willing to trade in all market condition. If this still sounds a bit abstract to you, let me give you two examples. The first example is when the market is very busy. For example, during the US election, where there's a lot of volatility in the market, many market participants might want to pull out the markets because of the volatility. So this is how we as market maker come in. We always provide the buy and sell prices to help the participants to make the trades. Another example is when the market is very quiet. For example, some instruments in some exchange might not get a lot of activity. In those situations, the buyer and the sellers might not come into the exchange at the same time. So again, this is where we, as a market maker, come in. We provide the buy and the sell price to help these buyers and sellers to make the trades. So that is what market making is. What does it take to be a successful market maker, though? So for us, data is very important because we need to make a lot of important decisions. First, we want to know which of our strategy is winning and by how much. We also want to know where the next business opportunity is. And we want to make sure that we are compliant with all regulations. Because of this, Databricks play a very crucial role in our success. We onboarded Databricks about a year ago, and it has now grown into a petabyte-scale data platform. We are also ingesting from more than 4,000 data sources in the form of Kafka topics or databases tables. And with over 500 monthly active users, it's getting clear that Databricks is widely adopted across the organization, and we expect all of these figures to grow by multiple times in the near future. So at Optiver, Databricks support key workflows across the organization. It enables our quantitative researchers to perform analysis on complex data sets. It also powers large-scale data processing with ease. It supports our machine learning development, and it helps teams to build dashboards for insights and decision-making. And throughout this talk, I'm going to focus on the dashboarding aspect of this. So now I'm going to give you a brief overview of our dashboard journey. Let me take you back about 2 years ago. At that time, all of our data was on-prem. All the data was scattered across different databases in multiple data centers across multiple countries. There was no centralized data platform, and it makes things really difficult. Not only that, most of these databases weren't even analyticals. They were transactional databases optimized for operation workflow, but not for deriving insights. Not only that, there was friction everywhere, especially from transitioning from research into productions. Here's how it used to look like. Researchers would often prototype their code, often in Python, but to go live, the code often needs to be rewritten in C++, and that translation process slows down immensely. And if somebody wanted to build a new dashboard, they would need support from an engineer to visualize that either on a Windows apps or a web apps. So around that time, our system wasn't built for speed or iteration. Everything felt very slow. Everything felt very hard. Fast forward 1 year when we onboarded Databricks and everything started to change. We saw what I like to call a dashboard revolution. There was an explosion in dashboard usage across the company. Teams were suddenly building and sharing dashboard as if it was their second natures. And it wasn't just anecdotal. We pulled the stats, and it was clear that the usage of AI and BI dashboard has skyrocketed. Everybody was tapping into the data. And why is that? It was because access has finally become easy. This shift has led to the democratization of dashboarding. Now, you no longer need a developer to build or maintain a dashboard. If you have a question, you can just explore the data and build your own insight. Even more impressively, thanks to Spark and Databricks, queries that were once thought to be impossible were now done trivially by everybody. However, with great success came growing pain. About 8 months ago, we started to feel the cracks. Our dashboard were no longer being used for research or analysis. They were now start being used for live use cases where latency and reliability really matters. We saw an overcrowding of our dashboard. Dashboard was refreshing constantly, often within every second, and this put a huge pressure on our infrastructures. There was also a growing problem of versioning. Dashboards were changing very fast and often without coordination. And there was also a problem with the front-end performance. As our dashboard grew more complex, they need to render more data, and our dashboard users starting to notice slow loading time. So about 6 months ago, one of our trading desks approached us directly asking for help. Their use case has grown too complex for the old tool. They need something more robust. So we sit down with them and we gather the requirements. So they told us that they needed a single-digit seconds end-to-end latency. They also wanted a live refreshing dashboard. They also needed an easy way to go from research into production. They don't want to go back to the old world where everything needs to be re-implemented in C++. They also wanted fine-grained access control to make sure that the right people were seeing the right data at the right time. They also needed the ability to render a massive amount of data without compromising the front-end experience. So here's like an example of an end-to-end life cycle of our dashboard used to look like. So first, our data producer would start publishing data into our Kafka clusters. From there, we would have an ingestion pipeline that pull data from Kafka and write to Delta tables. On the visualization side, the researchers would use the AI and BI dashboard connecting to the SQL warehouse and pulling the data from Delta tables. So we sit down and we realized that to achieve the SLA that the trading team asked for, there were two main key areas that we could optimize. The first part is on the ingestion side, and the second part is on the visualization side. So I'm going to go a bit into detail about the optimization that we have done on the ingestion side. So for the vast majority of our data, we have a C++ app that pulls data from Kafka and lands arrow files into an S3 bucket. From there, we have an autoloader that incrementally loads new files and write them into Delta tables. The advantage of this design is that it's very efficient and very cost-effective. However, the original purpose of this pipeline was to optimize for throughput rather than for latency. So for very highly valuable data set, especially the ones that the researchers' dashboard relies on, we instead built a more streamlined pipeline where a structured streaming jobs would read directly from Kafka. This would remove many steps along the way to get the data into Databricks as fast as possible. And thanks to the data frame interface from Databricks, not much logic was actually needed to change. We mostly needed to switch the data source from S3 to Kafka, and the rest remains mostly the same. We also invest a lot of time to optimize Spark configurations. One of the first changes we make is to increase the partition values. So by default, Spark would map each Kafka topics partition to one Spark partition. So if you have a very large Spark cluster, there's a good chance that the cluster is going to be underutilized. So by increasing this mean partition value, Spark would provision more tasks to read from these Kafka topics partitions. So thanks to the increased parallelism, this significantly improves our throughput and latency. Another optimization that we did is to increase the amount of data output per fetch. What I mean by this is, by default, Spark would pull a relatively small amount of data per fetch. However, for our use case, where there's a relatively high latency between our Spark cluster and our Kafka cluster, these small fetches means too many round trip, too much overhead, and underutilized micro batches. So we decided to increase both of these values to about 10 megabytes. This allows Spark to pull larger chunks of data in each micro batch. We also decided to disable optimize write when latency is very important. So for those who are not familiar, by default, Databricks enable this optimized write feature, which tries to compact the data before they write to Delta table. So the purpose of this is to help with file management and downstream read performance. However, for our use case, this behavior introduced extra shuffle steps and coordination between the executors, and this slowed down our write time. And fortunately, we didn't actually have to make the trade-off between write latency and read performance, because when you use structured streaming with Databricks enable auto-compaction by default. This feature would try to compact all the small files when the cluster is less busy. So thanks to this feature, we were able to keep the best of both worlds. So we managed to keep low latency and very good read performance. We also decided to reduce the shuffle partition in Spark. So what I mean by this is, by default, Spark set these shuffle partition values to 200, but in streaming or small batch workloads, that's far too high for us. So this leads to unnecessary start scheduling, excessive overhead, and longer processing time per batch. For our use case, we noticed that all of these shuffle stages were actually from Spark reading the Delta transaction logs. Because of this, we know for sure that these tasks are very light, and we're confident of reducing these mean partition values. And you can see here the cluster become a lot less busy. Like all of this activity were just from all the overhead of scheduling this unnecessary task. Last but not least, we also reduce the structured streaming logs versions. So by default, Spark maintains the metadata and logs for the last 100 microbatches when using structured streaming. The downside of this is over time, especially for long-running jobs, this can lead to bloated checkpoints directory and degraded performance. By reducing this number, the number of microbatch logs, this would reduce the number of microbatch logs kept in memory and disk. So from all of our effort to re-architecturing and this parameter optimization, we were able to reduce our ingestion latency from single-digit minutes to single-digit seconds latency. However, in order to achieve this kind of SLA from the trading teams, optimizing the ingestion wasn't enough. We also need to optimize on the dashboard side as well. Because of this, we decided to perform some re-architecturing of our live dashboard. So at the core, we built a custom Dash app powered by Flask, hosted entirely on Databricks apps. So this gives us full flexibility. This means no extra infrastructure to manage. The Dash app would connect directly to the Databricks SQL warehouse. It would pull in the data and serve visualizations. So I appreciate that Databricks apps and Dash might not be familiar with everybody here. So I'm gonna just give a bit of an overview, some context of what they are. So Databricks app is a new feature from Databricks. So it allows users to create apps on Databricks. The kind of like the purpose of this is if you are able to run your own Python app locally, Databricks would make it very easy to deploy it to production without too much effort, and they would run exactly the same way. So they would take care of all the infrastructure and the deployment overhead for you. So this technology is mainly built for dashboarding and ML tools. Specifically for Optivers, there were many benefits. First of all is everything is hosted on the cloud. This means that we were able to get both high throughput and latency when querying the data. It also allows us to avoid the egress costs when transferring data to outside AWS. It is also very easy to use. It only takes a few command lines and about 30 seconds to deploy your apps from local to productions. Most importantly, it has good built-in access control. First of all, you can control the access on the apps level, just like how you would control like who can access your notebooks or your Databricks jobs and so on. But more importantly, it respects Unity catalog permission by default. So this is very important for us at Optiver. So at Optiver, we heavily use row filter when most users can only see a subset of our data due to compliance reason. So with this feature by Databricks apps, everything would just work by default. If somebody wants to see a visualization, they would only see the visualization of the subset of data they have access to. Next is Dash. So Dash is a Python framework for building visualization, and they were developed by Plotly. And the main usage of this is to help users to build dashboard, and it provides a lot of rich visualization in the front end. And like one advantage of Dash is that you only ever need to know Python, no JavaScript knowledge really required. For Optiver, though, it has a lot of benefits for us. At Optiver, it's starting to become a standard technology to build front-end web-based visualization. It also allows us to render a lot of data through its GPU rendering. It's when I try it on, it's like 10 to 100 times faster when compared to rendering without GPU. And it also supports the data frame interchange protocol when we can plug and play with various data frame libraries behind the scene. And I'm going to talk more about this point later on. Back to the original high-level design. We will also consider some alternative solution. When building this project, we were asking ourselves, is it better if we query everything directly from the Databricks SQL warehouse, like in the top diagram? Or should we stream and pre-aggregate everything first? What I mean by this is, in the bottom diagram, we would stream the data in, perform incremental aggregation, and write the pre-processed results into a Delta table. From there, the dashboard would query a very lightweight, already pre-aggregated tables. However, at the end, we actually decided to go with the first option, which is seemingly more naive. And let me explain to you why. So there were two main reasons for this. The first reason is user friendliness. One of our main goals for this project is to help users to self-service. So having an SQL as an interface is a lot easier for our traders and researchers to adopt compared to asking them to manage a few dozen structured streaming pipelines. It's also very easy to modify stuff on the fly. So if our traders want to change their signals, with SQL, they only need to update the logics. But if with structured streaming, they would have to redeploy the pipeline and backfill everything from the beginning, which is very slow and lots of friction. And it can handle unpredictable parameters as well. What I mean by this is a lot of our SQL logics takes in parameters from front-end inputs. So because of this parameter is very unpredictable, having them being interpolated within SQL is a lot easier than trying to anticipate this value in streaming. And another kind of counterintuitive reason is it's actually, for use cases, it's actually faster to re-execute this SQL query again and again compared to incrementally process them. So there are a few main reasons. The first is it allows us to avoid performance issues with structured streaming with state management. So we have seen this again and again when we scale structured streaming very large, when we need to do stateful joins across many big tables, for example, 5 or 6 tables with about 100 rows per second, 100,000 rows per second. This is when the structured streaming state store start to break down, and it's actually slows things down. Scaling, the easiness to scale is another main big advantage. So, for example, when the market become very busy and we get a lot of data, thanks to the serverless warehouse, it only takes a few seconds for Databricks to add a few nodes to our cluster. This kind of like allows to avoid all the headaches that we don't need to anticipate the load or the capacity of our cluster, which is very nice. Delta caching is another big advantage. For those who are not familiar, with Databricks, when Databricks query a data set from Delta, Databricks will cache the underlying Parquet files on disk. For us, it works very nicely because most of our data sets are time series append-only data. So if we need to re-execute our query every X second, the cluster actually only need to load the extra X second worth of data, and the rest of them is already cached on disk. So in practice, basically, the entire table only need to be loaded once for the entire day. And Photon is actually one of the biggest reasons that make our dashboard feasible to meet this latency, thanks to its very efficient execution engine and very efficient query optimizer. It's allow our query to execute several times faster compared to open source Spark. Let me give you an example of what I mean. So we have seen this kind of behavior again and again for our use cases. So in this example, we have two large data sets, dataset A and B. Both are about 100 million rows. However, the filter that you see at the bottom here would eliminate about 90% of the data from dataset A. Dataset A has no filter on it, but it is still part of the joins. So intuitively, you would expect this query to be very slow because the query engine needs to scan and suffer the entire dataset B in full, because technically there's no direct filter on it. However, Databricks analyzed the entire query plans and noticed that the filter on dataset B eliminates most of its data. Therefore, the join will only touch a small set of data on dataset B. So instead of scanning and shuffling the entirety of dataset B, Photon actually injects an implicit filter on it based on what it knows of what is needed after the joins. So on the right-hand side here, you can see it in actions. The filter in the red circle has been pushed down on the dataset B, even though we didn't explicitly ask for it. So thanks to this means that there's less data suffer, there's faster joins, and there's much more efficient query plan, and we didn't need to change a single line in our SQL query. Let's take a closer look on how it works behind the scene. So at the core of this optimization is something called a Bloom filter. So it's a compact data structure that allows Spark and Photon to quickly estimate whether a record would match without actually needing to suffer to do the full joins. So how it works is Photon adaptive query optimizer would use the runtime start to figure out whether the query would save time. And the query optimizer would only apply only if one side of the join is very small and selective. This allows us to avoid shuffling unnecessary data, which in this kind of distributed query engine would compose the majority of the time spent. First, this allows us to increase the query performance by multiple times. So if you want to go a bit deeper in these topics, the team behind Photon actually published a great research paper here, which explained the inner working of how this works. So if you look it up on the internet on the title of this, Adaptive and Robust Query Execution for Lakehouse at Scale, you'll be able to see how it works in detail. Next, I'm going to talk about several optimization on the dashboard side as well. So as we work on this project, we know that there's a few problems that we need to solve. First of all, we need to find a way to easily manage our growing number of dashboards. As time goes, the number of dashboards that we need to be managing grow to about several hundreds. We also want to need to find a way for researchers and traders to easily modify it as well. And we need to find a way to reuse SQL queries because dashboard overcrowding was becoming kind of a big problem. So to solve this dashboard exploring problem, we built something called a dashboard generator. So it's a tool that turns modular config into a fully interactive dashboard. So on the left here, we have two components. First is a toml file that defines first the inputs, like dates or sampling rate, and then the definition of the graphs that need to render. For example, the query key, the layout, color, groupings, etc., all in a declarative way. We also have an SQL file that defines the actual query logics, which is parameterized and reused across multiple dashboards. So together, these two fit into our dashboard generator, which produce an input form with sensible defaults, a set of standardized visualization, a live interaction through a callback layer connecting to the Databricks SQL warehouse. This design brings several benefits. First, the dashboards are modular and easy to maintain. SQL logics are now being reused and not duplicated. And dashboard changes are now being made in config instead of in code, which is more accessible to our researchers. As mentioned before, one of the problems we faced previously was a dashboard overcrowding problem. This happens when multiple users triggering the same heavy SQL query. So at that time, our Databricks SQL warehouse would end up being overloaded because they need to re-execute the same logics again and again. So to solve this dashboard overcrowding problem, we introduced a log and cache mechanism. Here's how it works. So when we have multiple users needing to hit the dashboard at the same time, they are all trying to trigger the same query. However, instead of letting all of the requests go straight to the warehouse, the apps would instead first check a disk-based cache. If the result is still fresh, maybe within a certain set of TTL, we would serve it immediately. If not though, the app would try to acquire a log. Only one of these requests would go through. That one claim the logs and run the query, and once that's finished, it's gonna write the result to the cache. What about the rest? The rest of the requests that we wait, eventually they will get served from the cache when the cache is updated. So the benefit of this pattern is that it reduces the redundant queries. It prevents the warehouse overloading issues, and it's dramatically improves our dashboard responsiveness when there's a lot of concurrent users. I also want to highlight some of the recent innovations in this data engineering space that allowed this dashboard to work really well. So the first is a recent features from the Databricks SQL warehouse called Cloud Fetch. It would allow us to stream very large query result efficiently with high bandwidth and low latency. Polars is another recent innovation. It's a new data frame library that can handle transformation with zero copy rate. This allows us to reshape and filter the data without memory duplication. Dash recently also integrated with a library called Navos. So Navos gives us an abstraction over different underlying data frame library. Up until this change, if you pass in a data frame, any kind of data frame to Dash, Dash would actually convert that into a pandas data frame, and then it would render the visualization. Now, thanks to this recent improvement, tools like Dash no longer strictly relies on pandas. This means that we can plug in Polars instead for faster transformation performance and lower memory usage. And tying this all together is Apache Arrow. It's a standardized columnar format that makes this component interoperable by design. So here's how it comes together. So first, we have the Databricks SQL warehouse using CloudFetch to send large query result directly to S3. And then we would stream this result directly to the disk cache that I mentioned before. From there, we would load the data into Polars using zero copy read for speed and efficiency. Then, thanks to Navos, we can plug Polars directly to Dash, and now no longer conversion to Pandas is needed. The result is that we have a fast and fluid dashboard that scales from the back end to the front end. And this whole workflow works because of the shared columnar format powered by the Apache Arrow. This enables seamless performance across our stacks. So as the result, thanks to our optimization both on the ingestion side and the dashboard side, we were able to reduce the latency from single-digit minutes to single-digit seconds. And traders now can see data faster and react to the market trends more efficiently. It also allows us to free up developer time, so now they can spend more time to work on other initiatives. And we have been receiving overwhelmingly positive feedback from our traders and researchers. And if any of the things that I described sounds very interesting for you, we are actually hiring for great software and data engineers. So if you like to work on petabyte scale data platform and low latency data pipeline, feel free to reach out to me or visit our career page. And thank you for the talk, and let me know if you have any questions.